this is the housekeeping stuff that I wanted to discuss with you guys this week. On 9, everyone, no matter what session you're in, you've got something due, okay? And it's usually more than one something. So keep that in mind. Don't wait till the last minute to do those, although we're kind of at the last minute now if you haven't started yet, since it's due tomorrow. Tomorrow, or Thursday, the 14-week kids will take their Newton's Laws test, and the 12-week kids will take their one-dimensional kinematic test. Make sure you guys watch the reviews that I've recorded for those two tests before you take your test. I think they'd be helpful. At least I hope they're helpful. That's why I do them. On Friday the 29th, the 18-week kids will take their application of Newton's Laws test. Again, watch this video, but also watch the video I made last week, because that one also relates to the application of Newton's Laws unit as well, and hopefully it's helpful to you. On Monday, the 16-week kids will take the same test. They're starting to catch up to the 18-week students. Soon, they'll be doing exactly the same thing. On the 4th, next Wednesday, the 12-week kids will take their 2D motion test, and that's pretty important because since it's a Wednesday, that's a due date, which means the day you're scheduled to take your test is the day it's due. You can't just say, well, it's scheduled for Monday, but I'm not going to take it till Tuesday or Wednesday. It's scheduled for Wednesday and it's due Wednesday. So if you get behind, you're going to have a test to be working on as well that last day. So keep that in mind. Now, let's go to this this section, and I want to go back so you guys hear what I said at the beginning. Okay, so these are the formulas I went over last week. So if you are working on making a formula sheet for all of your units, you'd want to put this formula on there. I solved problems with each of these formulas last week. So go back and look at last week's recording if you want to see me solve a weight problem. A friction, if you want to see a friction problem, again, go back to last week, and I've solved a friction problem there. Okay, but these are your formulas. Tension, same thing. I solved a tension problem last week. Something I have been getting questions about. Tension is only for ropes, strings, or wires. You won't use tension for anything else. So keep that in mind. That's a question I've been getting this week. Springs, F equals negative kx. I've seen an error in the actual content of the course. Make sure that you're keeping this negative in here unless you have a good reason to take it out. And a good reason to take it out would be, for example, if your k was negative and it canceled out, or your x was negative and it canceled out. Otherwise, you need to keep this negative in here. I know there's some errors in the course where they don't have it in there, and I'm working on getting those errors fixed. And then our systems and slopes. So if you've got an object, let's say we've got this object right here, and let's say this is horizontal. I'm just not very good at drawing straight lines. So your normal force would be pointing up, your gravity force would be pointing down. Your applied force would be in the x direction one way, and your friction would be opposite the applied force. If you wanted to do the F net for that object, it would be the sum of all forces acting on the object in each direction. So for example, in the y direction, you'd have your normal force minus your gravity force because they're opposite each other. And in the x direction, you'd have your applied minus your friction because they're opposite each other. And then just another kind of convention type of thing, I like to write F net. Again, you guys know I like to write the subscripts like this, where in the course they just bear a big N for normal and things like that. When they say the normal or the net force, they'll just write this sum or the sigma and then F. So just keep that in mind. That's what they're doing there. They're basically writing the net force. They're just not writing F net. And that's just something that I like to do. Now, the problems for this section are difficult. And there's a couple reasons why. Like for example, this one, we've got two objects, not just one. We have an object in this X direction and we have an object in the Y direction. They are connected by a rope or a wire or something. It looks like a rope. And so, you know, we've got a tension force working with us here. So we've got a lot of stuff going on in these problems. So I think these systems and slopes problems are pretty difficult. So just kind of, when you see one, just slow down, take your time, and work your way through it. Just me personally, I actually don't even like doing these problems because I think they're really tedious, and I try not to make a mistake, but sometimes I do. So I'm going to underline what I know. This is the mass of box A and B, and then there's this coefficient of friction between box A and the table, and I'm just going to write that there. And so now they want to draw the free body diagram for each one. So I'm going to draw the free body diagram for A, and then I'll draw the free body diagram for B, and I'll try and do them in different colors just so you can keep them kind of separate from each other. So this is our object. This is A. So this is the object that's sitting on a surface. Since it's sitting on a surface, it's going to have a normal force directed perpendicular to the surface. Okay, and it's going to have a weight directed downward. Okay, it's going to have a tension force in this direction. Okay, so instead of an applied force is what we'd usually see in one of these diagrams, it's going to be a tension force because we've got that rope right there. Okay, and then we'll have a friction force here. They didn't tell us to ignore friction, so we've got to keep it in there. So these are our four forces acting on box A. Now let's do box B. Okay, so box B is in the Y direction, all of its forces, and it's not sitting on anything, so we don't need to draw a surface. Okay, and it's not going to have a normal force because it's not sitting on anything. In this direction, we're going to have a tension force on this object because you see we've got that rope right there. So we're going to have a tension force, and then we're going to have the weight. So this object is going to have just these two forces acting on it. Okay, so those are our free body diagrams for those two objects. Okay, now let's go to the next one. Okay, so what I did here is I went ahead and I already drew those free body diagrams on here. And then I also wrote what I know, and I put the little picture here. And then now we're just going to talk about the equations that we're going to use for each one. Okay. Again, you see how I'm breaking it up really slow. I'm going to use pink again for my A because I already used it on the other slide. So let's do the F net in the X direction for A, and then we'll do the F net in the Y direction for A. Okay, so the F net in the direction, we're going to have our tension force minus our friction force. Okay, that's what's going on in the X direction. For the Y direction, we're going to have these two. So we're going to have our normal force minus our gravitational force, and these are the same. And so this is going to have, this net force is actually going to be 0. Okay. Then we can do box B. So let's go over here, and we're going to just, and box B is only in the Y direction. Okay, so we don't have to even worry about the X direction, box B. And so we're going to have these two. Okay, we're going to have our gravity force minus our tension force. Okay, so those are our equations for each box. Okay, now Let's go to the next slide. Okay, so now we actually need to do some math. Okay, so the first thing it asks us to do is to calculate the weight for box A. Okay, so I'm going to draw a 1 here, and I'm going to calculate my weight for box A. Now, our weight is equal to our normal force, and weight is equal to mass times gravity. Okay, so my mass of my box is 75 kilograms, and gravity is 9.8, right? And we have that memorized. So then we'll have 735 newtons. Okay, now for box A, I'm going to use a different color just so you can, keep these separate. Now we need to calculate that friction force for box A. Okay, so what is friction? Your force of friction is your coefficient of friction times your normal force. Your normal force is equal to your weight, right? So they told us our coefficient of friction on that first slide. They told us our coefficient of friction was 0.250. And we just figured out our normal force was 735. So our friction force is going to be 183.75 newtons. Okay, and then the last thing it wants is Fg, or the weight, for box B. Okay, and why they're asking us for these is because we're going to actually use these numbers a little bit later. So we're just going to go ahead and calculate them now. So we've got them ready to go. It looks like box B is 40 kilograms, and then the same G, 9.8, because we're on Earth. So that's going to give us 392 newtons for box B. Okay? So far, not too bad, right? Okay. Now, here we go. Now they're going to ask, here we've got our equations, right, that we had, and now we're going to have our, we're going to go ahead and we're going to start kind of getting more into the nitty gritty of these type of problems. Okay, so they want to know the acceleration. So we only need to talk about the moving parts. Okay, so moving for box A is the x-axis. And then moving for box B is the y-axis. Okay, so that means for box B, we're going to use this formula, which is the only one we have anyway. And then for box A, we're going to use this formula because this is the only one where we're moving. Okay, so let's figure out what's going on. So to find the acceleration, we need to do F net A plus F net B. Okay, so in the for F net A, we're going to have Ft minus Ff plus whatever our F net for B was, which was FT minus FGA. Now I'm going to write it the other way just because it makes more sense the other way. So I'm going to do FGA because that's more than our tension force, and then FT. Okay, because if FG wasn't more than the tension force, then they wouldn't move, right? This would stay here and this would stay here, and they would just be like kind of chilling or whatever. But since we know there's a friction force here, they has to be moving. You know, they have to be moving in this direction, and so this G has to be more. Okay, so that's just going to make it a little easier for us later, or now. So now we can go ahead and let's cross these guys out. So we've got FT positive, we've got FT negative, so we can get rid of those. Okay, and then what I'm going to do here is, what is F net really? Our mass times acceleration, right? So I'm going to do mass of A times the acceleration plus the mass of B times the acceleration. And then I'll have, on the other side, I'll have, oh, sorry, this should be a B. I was like, I don't remember it spelling Georgia before. Should be a B because we're talking about box B. Okay, so then we'll have F, our weight of box B, minus the friction of box A. And I know this one was first. I just, swapped them because that one's already a positive, so it just made it a little easier. And then what I'm going to do here is I'm going to kind of separate these out a little bit. And I'm just keeping with the colors just so you can kind of see, where each number or each, thing is coming from. Okay. So now what I'm going to do is I'm going to go ahead and I'm going to plug in some numbers just because I think it'll make it a little easier for me, or if you're solving it for you. So I'm going to have A is 75 plus 40 equals, we already had our GB, right? We got that, which was 392. And we already got our friction force as well. So that was kind of nice that, like, at least we're not like at the last minute, having to go solve for friction. We already did that. I'm not getting my pink color to stay up. There we go. Okay, so what I'm going to do is I'm going to add these two together. So I'm going to get 115. And then I'm going to take the difference between these two. Now I can go ahead and I can divide both sides by this. And then my acceleration is going to be 1.81 meters per second squared. Don't forget your units, right? You did all this work. You don't want to forget your units. Okay, so there we go. That's how we get our acceleration of our system for this one. And then now they're going to ask us one more thing because, you know, we haven't been doing enough with this problem. So now they want to know the tension on the rope. Okay, and so there's two ways you can solve for tension because you've got two formulas that have tension in them, right? And both of them give you the same answer. I actually tried it. I'm only going to do one here, and then you guys can do the other one if you want. But basically, you can use this formula because it has a tension in it, or you can use this formula, but it should be FG minus FT if you use this one. But so anyway, I'm going to go ahead and use the x-axis one, box A, just because it's, you know, it's box A and I've already got it. But you literally could do either one. Like I said, I tried it, and I got the same answer for both. I just got kind of bored of pink and green. That's why I switched to the blue. So right now I'm just kind of, you know, doing algebra. I'm just getting tension all by himself on one side. That should not be equals here. Okay. Okay, so now I can go ahead and I can do, you know, I can put my numbers in here. Whoa. I'm just gonna, well, I didn't actually put numbers. I just exchanged F net for mass times acceleration. Now I'm gonna put numbers in here. So my mass is 75. My acceleration is 1.81, which we got yesterday, or we got on the last slide yesterday. I hope this problem doesn't take us 2 days, although it kind of feels like it's taking long. And then we'll have 135.75 plus 183.75 equals FT. Add these together, and we'll get 319.5 newtons is equal to our tension force. And like I said, if you want to try it for box B, you'll literally get the same answer. Well, I got 319.6, but you basically get the same answer. So, you know, either one of those is fine. And now we are, I believe, yes, finally done with that problem. So you can see that those systems and slope problems, you just have to slow down and kind of draw your free body diagram. They really do help, even though they're kind of annoying. And then you just have to slow down and just kind of work your way through it step by step by step. So in this problem, they actually told us, solve for this, solve for this, solve for this, solve for this. Like draw the free body diagram. What are the equations? You know, what's the gravity? What's the weight? What's the tension or the friction force? What's the acceleration? What's the tension? It's possible they could just say, what's the tension? And then you'd have to go through all those steps on your own. That wouldn't be very nice, but they could do that. So just, you know, keep that in mind. Now we're going to go back to circular motion. We've already done a little bit with circular motion, and now we're going to kind of come back to it. We've already had the formula on the bottom. Centripetal acceleration is equal to v squared over r. But now we're going to talk about also centripetal force, which is mass times your centripetal acceleration. So, and so a lot of these problems you have to solve for your centripetal acceleration and then solve for the force. So it's kind of like a two-step problem. Okay, so let's try this guy. So in this one, let me pick a new color. Orange sounds fun. It's almost October. So we're going to have a car with a mass of 1850 kilograms, and it's going around a curve that has a radius of 50 meters. So that's going to be our R. And then it says, what is the force of friction acting on the car if the coefficient of friction is 0.3? Okay, so here's what we've got. Let's write what we know. We've got our mass, we've got our radius, and we've got our coefficient of friction. Okay, so the first thing we need to do is we need to, we need to solve for the friction, right? So to solve for friction, we have the coefficient of friction times the normal force, right? So now we need to solve for the normal force, okay? So that would almost be like step 0. If I do that, it's not going to look like there, step 0. And our normal force is equal to our weight, which is just mass times gravity. So then we can do that 1850 times 9.8. We're going to get this huge number because, it's a car. It's heavy. And then we can go back and we can put that number in for our friction force. So I'm going to do 0.3 times 18,130, and I'm going to get 5439 newtons as my friction force. Okay, so I've gone ahead and I've solved this part of this problem. Unfortunately, this problem has a couple slides, which seems to be the norm when we're talking about this the systems and slopes unit. Okay, so same problem, right? But now they want the maximum velocity the car can go around the curve. Okay, so that's going to be when our centripetal force is equal to our friction force. Okay, so our centripetal force is equal to our mass times our centripetal acceleration, which then we can put in here, we can do mass times v squared over r equals our friction force. Okay, so this is kind of the formula that we're working with. Okay, so now what I'm going to do is I'm going to multiply this r by both sides. So I'm going to get mv squared equals my force of friction times my radius. And then I'm going to divide both sides by m. And then I'll have my force of friction times my radius divided by my mass. Okay, now, and you could go ahead and you could do square root. I don't know, I don't like to do that. I feel like square roots are messy, so I don't want to write them any more than I have to. So I'm just going to have v squared equals, and I'm going to go ahead and I'm just going to write my numbers in. So my friction force was 54.39, and my radius was 50, and my mass was 1850. Now, before you just go ahead and plop this in your calculator like this, be aware. If you put this in your calculator like this, you will not get the right answer. Your calculator does not know that you want to multiply these two things before you divide. Okay, so if you want to put this in your calculator all at once, you can, but you're going to need another set of parentheses here. Okay, that'll tell the calculator that you want to multiply these two things before you divide. Okay, so and then what did I get? I got 271,950 over 1850. Then now we've got v squared, right? So we need to take the square root. I know this is kind of messy, I'm sorry. So we have v equals the square root of 147, which is 12 meters per second. Okay, so that's our maximum velocity that we can go around the curve. Okay. Now this last section of this test or module or whatever, it's Newton's law of universal gravitation, and it uses this formula. Okay, now there's a couple things that I would make sure to kind of know, and one of them is big G. Okay, so little g is what we've been using, and that's 9.8 meters per second squared. Big G is 6.67 times 10 to the negative 11. Okay, and that's a constant. You can look it up, so I would just go ahead and write that on your formula sheet, memorize it, whatever you want to do. But that's something you're going to need for all of these problems because, see, there's a big G in the problem. Okay, and same thing kind of as the last slide. If you're going to do these problems and you want to put it in the calculator all at once, you're going to need to put a parentheses right here. Okay, that'll multiply these things before you do this. And then I would also, I would put a parenthesis here. And that'll make sure it does the math right, your calculator anyway. So, and then the distance to the center of the Earth, this is just here because a lot of these problems are on Earth, and it's from the distance or the radius is based on like from the center of the object. So if you're on Earth, you need the center, the distance to the center of the Earth as well. But a lot of times they give that to you. Like in this one. And so let's try and solve one of these problems. Okay, so we have an astronaut. He's in geosynchronous orbit around the Earth. Wow, that sounds really difficult, right? We could totally erase this sentence and it would not affect our problem one tiny bit. Okay, so if you see all these big words, don't freak out. Okay, so the orbit is 35,786 kilometers above the Earth's surface. Okay, so we're going to need the radius of the Earth plus this. And then we have a mass of 65 kilograms for the little guy. So that'll be mass 1. And then now they're telling us the radius of the Earth. Remember, we're going to need to add these two things together. And then we have the mass of the Earth, so that'll be our M2. So then it says, what is the radius of his orbit? Okay, so this is the first part. This is where we're adding these two together. Okay, the first thing we need to do, our radius is going to be the radius of the Earth plus that 35,786. I'm just calling it that because I don't really even know what to call that. And then this is in kilometers, and so is the Earth. So we're going to need to take both of these and convert them to meters because these problems need everything in meters. Okay. So I'm going to have 1,000. What's the kilometers? Sorry. I was like, wait a second, I'm going to end up with kilometers. That doesn't make sense. So we've got kilometers over here, and then we'll have 1 kilometer on the bottom, has 1,000 meters in it. So then these kilometers will cross out, and we'll have 3, 5, 7, 8, 6, 0, 0, 0. And I'm, so what, 35 million. And then we have the radius of the Earth, which is the 6378 kilometers. And we'll do 1 kilometer, 1,000 meters, same as the other one. So we'll have 63,780,0. So we'll have 6 million here. And these are both in meters. So then we'll just add these together. Okay, so I'm going to have 35786,000 plus 6378000, and so we'll get 42,164,000 meters. And then what I would do is I would go ahead and just put this in scientific notation. So it's 1, 2, 3, 4, 5, 6, 7. And I would write like that. Just because it seems easier to me. But you know, if this was a short answer question on the test, either one of those answers would be right. I'm not going to take off because you didn't put it in scientific notation. And then let's see what's next. Okay, so now they want the weight of the cosmonaut at this altitude. Okay, so that would be his FG. So now we're actually going to use that weight formula. Okay, so, or this Newton's law of universal gravitation formula. So we're going to have G, M1, M2, R2. Okay, so I'm going to go ahead. I'm going to move it over here because there's a lot of stuff we got to write, right? I'm going to go ahead and put my big parentheses so I don't forget. I'm going to put G in here, 6.67 times 10 to the negative 11. And that's my constant, right? That's just something I've got written on my formula sheet or whatever. It's not something that I've memorized. Or, I mean, you could memorize it, but it's not something that they gave us. I'm putting the 65 for the mass of the astronaut, and then the mass of the Earth, the 5.9723 times 10 to the 24. I'm going to put my extra big parenthesis there, and then I'm going to draw my fraction line. I'm going to put another parenthesis here. And I'm going to write my 4.2164 times 10 to the 1, 2, 3 to the 7. Square it. And I'm going to put another parenthesis here, just in case I decide to put everything in my calculator all at once, which I'm not going to because I don't like to do that. But just in case I do, I'm not going to mess it up. Okay, so now I'm going to multiply all these things on the top together. I'm going to get this number. And then when I square the bottom, I'm going to get this number. And then when I divide these two, and again, because these have exponents in them, I would go ahead, if you want to put it, and I would go ahead and put parentheses, but I'm kind of like a parentheses freak. I like to put parentheses everywhere. And then I get his weight, which is 14.57 newtons. So that's that problem. So this is the end, basically, of the application of Newton's laws unit. You can see that the problems that we did this week, if you've already watched last week's video, you can see that the problems this week are much more, they have more steps than the problems from last week. So I guess if you're already watching this video, it's not really going to help, but I recommend watching the other one too, just because it kind of leads in to this one with like the net forces and like how to calculate tension and that kind of stuff, and then it leads into these more difficult type problems. So the best thing I can say for these problems is just slow down and just work it very slowly, and work your way through it. And then that means, on your test you might not get a ton of time, right? Our tests don't they don't want you guys like looking up the answers online, basically. They want you to kind of know how to do it when you go into the test. And so if you're going into the test and kind of struggling and like, oh, I don't know how to do this, and like trying a bunch of different formulas and things like that, you're probably going to run out of time. So I would make sure that you know how to do these problems backwards and forwards before you take the test. And for me, when I was in school, I would probably do the practice problems 3 or 4 times. I would do it once, and I'd have to look at, exactly the key over and over, right? The second time, I might have some of it down, but I'd still have to look at the key to see like what the next step was. The third one, I'd have a lot of it down. And then by the fourth one, I felt like I couldn't write it down fast enough because I knew all the steps. And so you may have to do it over and over and over. And it's okay if you're doing the same problem over and over, because what you want to learn is the steps or the pattern. And so, even if you're like, oh gosh, I only have so many practice problems, that's okay. You can do those same practice problems over and over, and it will help you. So, just make sure that when you go into that test that, you know what you're doing. Because if not, you may run out of time.